Well, why do we even use tangent lines? And this has been briefly discussed in another video, but here goes. Let's zoom in. There you go. Notice that at this point, the parabola and the line seem to coincide. And they don't. They actually only meet at that one point. But they are so close in that general area, you know, around in here, just super close to where if I wanted to simplify any computations for the parabola, I could just use the line, and that would be so much easier. So if I said, hey, what's the value of the function at a number really close to 2, like, not 2, but 1, really close to 1, like 1.0001. Well, you'd take 1.0001 and you'd square it and you'd add 1 and you'd get the actual value of the function. But you know, an estimate that would be not perfect, but very ridiculously close would be just to plug it in here. Because this is the equation of this line, which is super close to the parabola at that specific point. So in that neighborhood of that point, you can use it to make approximations, which we're about to do. So write the equation of the line tangent to this at x equals 2, and then we'll just stop right there. There's more that we're going to do, but let's just start by doing what they asked, which is a beautiful thing when we start writing down stuff and then filling in everything that we know and don't know and all that stuff. So y minus something equals m, and then x minus 2. So here's the x value we're dealing with. And we're going to plug in a 2. So f of 2 is going to give me 1/2. So y minus 1/2. There we go. Equals, well, the slope. Okay, well, what's the slope of the function? Well, the original function is... and I'm going to switch colors here. If you want to do a rewrite on this function, it's really x to the negative 1. So the derivative of the function is still the derivative of that. So let's change that, put an apostrophe there. That way we have f prime of x, and that is equal to negative 1, x to the negative 2. That's negative 1 over x squared. That's good to know. Should have switched colors here. I need to know the slope at 2. So f prime of 2 is negative 1 over 2 squared, which is negative 1/4. That's going to go right there. Okay, what in the world does this mean? It means that at the point 2, we can draw a line, and that line's going to go around here somewhere. We'll find out exactly how to draw it in a second. But let's finish working this out. So y minus 1/2 equals 1/4 x minus 1/2. We will, something's wrong, something's wrong, something's wrong. Something seems very wrong about this. Oh, yeah, that's, yeah, negative right there. That's negative, which makes that positive. There we go, fixed, 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 fixed. And so we will add 1/2 to the 1/2, and we get, well, 1. Okay, so here is the line that we're dealing with. That's it right there. Okay, so in the general vicinity of 2, we can use the tangent line to make approximations because it's a lot easier, in some contexts, to just plug it into a linear equation than something that's a little more complicated. Like 1 divided by something is kind of complicated, but negative 1/4 times something plus 1 isn't as complicated. So we have a little bit more to do. Use your tangent line to approximate the value of f of 1.9. So over here, using a different color, just so it doesn't all run together, we're going to say that f of 1.9, I'm not going to say it equals, because they said approximate it, so we're going to say it's about what? Okay, well, exactly would be 1 over 1.9. Good luck with that by hand, right? However, we can do this one, 1.9. and then plus 1. I'm plugging this into the equation of the tangent line because, and I can, because 1.9 is in the neighborhood of 2. So 1.9 is back here a little bit. 1.9 is about right here. So 1.9, you know what? The line and the curve are so close together that whatever I come up with here is going to be ridiculously, ridiculously close. So I am going to cheat a little bit. I've used a calculator, and I got negative 0.525, and it's okay that we do that. Totally okay. But now it's saying, is your approximation an overestimate or an underestimate. And now we are stuck trying to say, well, okay, is this lower than the actual value? Now, I could cheat again and use a calculator and compare it, but let's not. Let's actually not do that. Let's look at the graph. Okay, if they would have asked, use your approximation, use your tangent line to approximate the value of the function at 4. Okay, would the value of the function at 4 be greater than or less than the value of our tangent line approximation at 4? Okay, hopefully you thought it was greater than. If you didn't, that's okay. So here's the deal. Here's 4. The tangent line is here. The actual curve is here. Here's why. The curve itself is curving upward. There is a phrase for that. You're going to hear it a lot later on, but it's called concave up. Let me draw this kind of in an exaggerated way. If I have a line and I have some curve that does that, and this is very exaggerated, it's not the exact same contour, but the idea is the same. If I say, well, you know what? I want to know what happens at this specific value. So here's my approximation, here's the actual curve. Is my approximation over or under? It's under. So when my curve is over the line, my line is an underestimate. If my curve is over the line, if my curve is under the line, then my approximation is an overestimate. Okay, when you see it, you get it. Here goes. My line is under my curve, so I have an underestimate. I may have worded it funny, worded it confusingly, but this is an underestimate. They didn't say why. We're going to get into specifics on that later. Underestimate. There we go.